In this movie, we're going to talk about ligand field theory to describe the bonding in a metal-ion complex using octahedron complex as our example. Ligand field theory is essentially a combination of crystal field theory and molecular orbital theory, except the difference being that in crystal field theory, the interaction between the metal and the ligands is considered purely electrostatic. In ligand field theory, we take more of a molecular orbital approach to describe covalent bonding between the ligands and the metal. And so we use combination of the atomic orbitals on the metal and the frontier orbitals holding the lone pairs of the ligands to produce a molecular orbital description of the bonding in the complex. So much of the terminology between crystal field theory and ligand field theory will be similar. And in fact, what we'll see is that the splitting that we get between the d orbitals from the molecular orbital or ligand field theory approach will be the same as we found in the crystal field approach. So in an octahedral complex, we'll get a d orbital splitting like so. However, the ligand field approach it's a little more realistic because it describes a covalent bonding between the metal and the ligands and gives us more information to work with in describing the properties of the complex. So for an octahedral case, we're going to need our octahedral character table because the method for producing the MO diagram for this complex is similar to what we've seen already when we worked with molecules like water or ammonia. We're going to use the atomic orbitals on the central atom, in this case the metal, and the ligand frontier orbitals combined to various symmetry groups. And we're going to combine those based on their symmetry properties to create the molecular orbitals for the complex. So the first thing we're going to do is ask what d orbitals in the metal can be used in bonding. Well, let's assume a first row transition metal. So in that case, we have our 3d orbitals, 5. We have the 4s. And we have the 4p. And I've arranged these essentially in the order that they would be found in energy in a complex as opposed to, of course, the free ion. Next, we want to assign symmetry labels to those d orbitals. So we want to know what are the symmetries of the d orbitals of the metal. Well, the symmetry of the orbitals in the metal, since it's a central atom, can be determined simply by inspection of the character table. Of course, we could imagine a dz squared orbital or a dx squared minus y squared orbital on this, perform all the symmetry operations, right, and find, of course, where it fits in terms of what irreducible is produced when I perform all the symmetry operations, but at this point it's easier just to inspect the table directly. So the s orbital of the central atom always takes on the most symmetric representation, which for an octahedral complex is A1G. And so we're going to put A1G label below our 4s orbital in the diagram. We also find that the dz squared and dx squared minus y squared orbitals will have EG symmetry. So we're going to place an EG label between below 2 of the lines on our d orbitals, representing the dx squared minus y squared and the dz squared. We also find that the dxy, dxz, and dyz have T2G symmetry in this octahedral complex. So we'll add a T2G label below 3 lines on my d orbitals And then finally, we see that the px, the py, and the pz orbitals should have T1u symmetry, and so we add a T1u label right underneath our 4p orbitals for the complex. Next, we want to consider the nature of the ligands orbitals, which are holding the lone pairs. Now, ligands can interact with the metal via sigma, right? So head-on interaction, or a pi interaction. We'll talk about pi interactions later on. But for now, we're going to look at the ligands just from a sigma donation approach. So we have the lone pairs in the frontier orbitals of these ligands, and we're going to look at those as sigma donors, which makes the production of our reducible representation, i.e. the combinations of these frontier orbitals to produce our group sets, making that is pretty simple for a sigma donation. So we have our ligand orbitals. I'm writing 1, 2, 3, 4, 5, 6 ligand orbital, group orbital sets down here, which will be representing the various combinations of our frontier orbitals to produce those groups. We're going to produce a reducible representation, reduce it, and then determine the symmetry properties of the various groups. So in an octahedral environment, 6 ligands, the E operation will leave all of those sigma donor orbitals unmoved, so they don't translate in space, which means they'll all have 1s for their characters. And so we get a 6 under E for our reducible representation. For our C3 rotation, the C3 axis goes right between the triangle produced by L1 to L4 to L6 through the triangle produced by L3, L5, and L2, right? So the rotation rotates L1 into L4, L4 into L6, L6 into L1, and of course the same down here for these. So they're all moved in space, so they get a 0 for their character. The C2 axis goes between the bonds in the octahedral case. So this C2 axis represents a bond, sort of an axis bisecting these bonds. So when we do that rotation, everything will be moved in space. So imagine an axis that is right here, L1 and L2 would flip, right, would change positions, right, along with L5 and L4, and L6 and L3 would change positions. They're all moved in space, so they get a 0 for their character. The C4 rotation is on an axis that goes through the bonds, right? So we have, of course, we have several of those rotations. There's 3 C4 axes, each with 2 different operations for a total of 6. So we'll just look at this one, an axis going through L1 down through L2, right, on those bonds. A fourfold rotation would move L3 into L6, L6 into L4, L4 into L5, and so forth. So these 2 are unmoved, these 4 are moved in space, which gives us a 2 for the character of the matrix that would describe that particular operation. And then the last one I'll describe in detail is this C2 rotation. Notice how it says C42. The 180 degree rotation on the what we called the C4 axis is a C2 rotation. So this C2 is the same axis as our C4, but we're doing a 180 degree rotation. And so in that case, again, 2 of our ligand orbitals are unmoved, and so we get a character of 2 under the C2 operation. Okay, so the rest of those you can pause here and try out to work out the character under each of the other operations for our ligand orbitals. And what you get is 0, 0, 0, 4, and 2. Okay? So the next thing we need to do is to reduce this. In other words, find out what irreducibles sum, what irreducible representations from our character table sum to give us this reducible representation, and therefore work out the symmetry properties of our various ligand group orbitals. I've started with writing out an equation to reduce this to determine how many A1G symmetry groups there are. So we'll just go through this quickly and then you can work out the rest of them. For this particular character table, the order, right, is found 1 plus 8 plus 6 plus 6 plus 3 and so forth. So the order of the group is 48. So 1 over 48 times, and these are slightly out of order from what is usually given in your text, but I'm taking 6, right, which is the character of our reducible representation, times 1, which is the character of the irreducible under the A1G, times 1, which is the number of operations, and then the next is 0, so 0 times 1 times 8 gives us 0, 0 times 1 times 6, 0, and then 2, which is the character of our reducible, times 1, which is the character of the irreducible under A1G, under the C4 operation, and then times 6, which is the number of operations in that particular class. Taking that out, we complete the equation like this. It turns out to be 1 over 48. This sums to 48 and gives us 1 A1G symmetry set. So one of our ligand group orbitals will have A1G symmetry. Now, you can either try to figure out the remaining ones by inspection. We know that under E, right, we have to have some combination of irreducible representations that add to 6 under E. And what we find is when we go through the process further is that we have an A1G, an EG, and a T1U. Okay? So the symmetry of our ligand group orbitals are A1G, EG, which is a doubly degenerate set, so that'll be 2 of our groups have EG, and then T1U, which is a triply degenerate set. And so we can go ahead and put those in to underneath our ligand group orbitals. So now we know the symmetry of our atomic orbitals in the metal, we know the symmetries of our ligand group orbitals, and we can start to combine those to produce the MO diagram for the complex. So I'm going to rewrite this just a little bit. I'm going to add in my A1G, EG, and T1U ligand group orbitals like this. I'm separating them to make them a little bit easier to see. Sometimes you'll see them in parallel and sometimes written out like this. We'll also put in my metal atomic orbitals. Notice the ligand orbitals are lower in energy than the orbitals on the metal. Now we're going to combine orbitals of matching symmetry to produce molecular orbitals. We have the A1G of the 4s matches the A1G group. So we are going to produce a bonding and anti-bonding orbital. The exact placement of this line is, in this case, qualitative. So, but it should be above the original atomic orbital of the metal and below our A1G group orbitals for the ligands. So we get that combination. I'll write dotted lines to show which sets of atomic orbitals were combined to produce these molecular orbitals. Now, you are not required to produce, using symmetry adapted linear combination, the pictures of the more complex group orbitals. However, those will be given to you, which is nice because you can see what the group orbitals look like. So the A1G group orbital set looks like this. So it's a combination, right, of each of our sigma donor orbitals to produce this A1G group, and you can see how the symmetry of the s orbital matches perfectly with that and would be used to combine. We would use the A1G in our A1G group to produce a bonding orbital, and then subtracting these two to give the antibonding orbital. Next, we have the E1G on the ligands combined with the E1G, which remember are the dx squared minus y squared and the dz squared of our atomic orbitals in the metal. So we have an EG bonding and EG antibonding. And again, these need to go below the energy, right? The bonding should go below the energy of our ligands and above, right, the energy of our original 3D orbitals that were used to create our MOs. And we'll draw lines in to show which atomic orbitals combine. And of course, the EG is, remember we said the dz squared and the dx squared minus y squared. Here are the group combinations for our EG groups. So you can see what those look like and see beyond just matching up the symmetry labels, how the group orbitals and the atomic orbitals of the metal match perfectly. We would have this, the dx squared minus y squared plus one of our EG sets, right? Adding those to produce a bonding and subtracting the antibonding molecular orbitals. And then next, we have an interaction between the T1U set of the ligand groups and the T1U set, which is the PX, PY, and PZ orbitals. So we're going to put those in here and here. Okay, again, lower in energy, higher in energy, and draw lines in to show how the atomic orbitals were combined. And then here's the picture of the p orbitals of the metal and our group sets, T1U sets of our ligand groups. Combine this plus this to give a bonding, subtract to give antibonding orbital sets in the molecular orbital diagram. Okay, notice the T2G did not match. That's our dxy, dxz, dyz orbitals did not match any of our ligand groups in symmetry, so we just move those over into the diagram as non-bonding orbitals. Now, be careful to inspect your diagram. We started with a certain number of atomic orbitals, right, and atomic orbital groups. We should have that same number of molecular orbitals in our diagram. Notice in the diagram we've labeled the symmetry of our MOs, and we've labeled them all sigma because these were produced via sigma interaction between the lone pairs in the frontier orbitals of ligand, directly head-on overlap with the atomic orbitals of the metal. Notice that the resulting split of the d orbitals is the same as what we found in the crystal field approach. Here's our crystal field splitting. Here's a d orbital splitting from our ligand field approach. They're the same. But now we see, first of all, why we have sometimes you'll see in the crystal field approach, they'll label the lower set T2G and the upper set EG. Now it's easier to see why that's the case. In addition, we get more information. Now we know that our lower set of orbitals are non-bonding, and our EG set is actually an anti-bonding set, which is primarily d orbital in character, right? But anti-bonding, and that actually has a lot of significance when you start talking about bond lengths of the complex and redox reactions. The strength of the splitting, right, is called ligand field stabilization energy. So we talk about that in the same way as we did with the crystal field splitting. And stronger field ligands will cause a greater splitting, weaker field ligands a smaller energy splitting, resulting in high spin and low spin complexes. Okay, so now we'll talk about adding the electrons into the diagram. Since this is an octahedral structure, we have 6 ligands. Each ligand comes in with a pair of electrons. So we have 12 electrons that will be added to our MO diagram from the ligands. 2, 4, 6, 8, 10, 12. Those will go into the lower lying bonding orbitals, sigma bonding orbitals. Since these are all closer in energy to our original ligand group orbitals, these are primarily ligand orbital in character, with some contribution, of course, from the metal atomic orbitals. Anyway, we fill those in starting from the lowest energy, Ag, 2, and then through the Eg and up to the T1U. So you can see the lower lying bonding orbitals are all filled due to the ligand lone pairs. Now, the number of electrons that we add into the d orbitals, or what were formerly the d orbitals, are now our T2G and EG set. The number of electrons that fill into those depends on, of course, what the identity of the metal complex. So let's say we have an iron hexa-aqua complex. We'll say this is in the +3 state. Since water is a neutral ligand, that means that the iron is +3. +3 iron has 5 d electrons. So those electrons will fill in to the d orbitals here. Now, whether the electrons fill all in the lower T2G or distribute between the T2G and EG depends on the strength of our ligand field, which is dependent on several factors, including the type of ligand and the oxidation state of the metal, and so forth. We'll talk about that more, but let's assume that this is a weak field case. In other words, the splitting is small, and that is likely given that water, as we'll find, is a weak field ligand. So this splitting is small, which means that the energy to pair electrons here in the T2G is greater than the energy to have the electron go up into the EG. And so in that case, when we fill in our 5 electrons, they would be distributed like so. Okay, so our 5 electrons fill in, and this would be called a high field, a high spin case due to the weak field interaction between the ligands and the metal. Okay, and that completes the molecular orbital diagram and our ligand field theory representation of the bonding in this octahedral complex.